Welcome back to Reconstructing Relativity, Chapter 9. We're going to continue on topics of time skewing and synchronicity. Try to keep this shorter today, so I might need a part C or more. We'll see. Wow, so many ideas, so little time. But let's get started. And this is a picture from our bugs form plot, also known as radial motion graphic, in which the whole particle is moving to the right at a high rate of speed. And we're plotting through colors. The first 5 time steps are in red, then yellow, then 5 time steps in green. The energy inside the particle is slowly traveling to the right, finally makes it to its boundary and reflects. It only takes 2 steps to get back. So that's the way the particle behaves. And we're saying micro equals macro. So we can use this graphic to represent a similar situation for 2 observers, one at position A and one at position B, trying to synchronize their clocks. And according to Einstein, if a signal is sent from A and gets to B, B sends a signal back, records the time it received the signal. A records the time it receives the signal back. So in this situation, A sends a signal at 0. B gets a signal, it's got some time on its clock. If that clock at B happens to say 28, well, it's supposed to be 15. It's supposed to be, in order to be synchronized, it's supposed to be midway between A's sending time of 0 and A's receiving time of 30. So clock B should be set to 15 to be synchronized, which means if for some reason clock B's clock said 28, it has to dial it back 13 ticks so that it reads 15. So that's where we left it off last time, and we'll talk about this a little more. Now, if A and B clocks were truly synchronized, in quotes, you'd think that B's clock would read 28 at the arrival time, but true synchronization of this type is impossible. If it did read 28 when it arrived, then clearly the speed of light would be measured to be different in the 2 directions. I mean, it's the same distance both ways. It would take 28 clock ticks to go one way and only 2 clock ticks to go the other. So clearly the speed of light would be measured to be different speeds in 2 different directions. But Einstein sets it up in a way that, as we'll see, is very rational and practical, such that for clocks to be synchronized in their reference frame, the clock B time, the midway point of the cycle should be the midway point of the time. So 30 seconds total, B should be reading 15 at the point it receives the signal. So in some sense, if you could freeze the universe at a particular point in its existence, you'd see that clock A and clock B don't actually read the same time at the same time, if you know what I mean. In their frame of reference, as set up scientifically, they're synchronized. But in another sense, they're not. They're not reading the same time at the same time. And that leads us to this next concept. And this concept is what I call state universe. If the universe exists in a state in which event 1 has happened and event 2 has not yet happened, then event 1 occurred first in state universe. This is a philosophical concept independent of any measurement. And if you go into physics and relativity, this concept won't be there. And this is something I'm bringing in because it actually helps us to see what's going on. To have this point of view, our constructive model is talking about sort of as if we're gods. We can see reality. We can see what's happening without relying on measurement, we can think about what's going on and then look at how measurements occur in light of that reality. So this state universe is a useful concept philosophically, and we'll use it fairly often. For example, in this scenario, we would say that clock B, which is the leading clock positionally as the whole pattern moves towards the right, must set its clock backwards in state universe time by 13 ticks in order to be synchronized in its reference frame with clock A. Why did Einstein choose to set up clock synchronization this way? It's the only practical and logical way to do it. Here's why. Imagine there's two spaceships and they're traveling in the same direction at the same speed, and they're maintaining this distance of 1 light minute apart. It means that there would be ask a question, you'd have to wait 2 minutes until the answer came back. So communication was kind of slow. But they maintain the same distance through space. But the thing is, as we know from Michelson-Morley, they can't measure the speed, what their speed through space is. So there's a 2-minute delay between communications, but is it 60 seconds going one way and 60 seconds coming back? Or if it happened to be going 0.866 speed of light, it would take 112 seconds going one way and only 8 seconds coming back. Could be anything. Could be anything, and there's no reason to know. There's no way to. That's the key. There's no way to measure that, and so the only logical choice, it's going to be arbitrary pick. You might as well pick the even one, even each way. That's what Einstein did. And we know intuitively that different things are going on in these two ships at the same time, but there's no instantaneous communication. So, like, the example I like to think of is a New Year's Eve. They're both having a New Year's Eve party, and they're both kind of on the clock. 3, 2, 1. Pop the cork. Are they really popping the cork at the same time, or is there a state of the universe in which the people in ship A have popped the cork and the people in ship B have not yet popped the cork? That's the concept of state universe time versus frame of reference synchronization. If they had instantaneous communication, then they could truly synchronize their clocks in state universe time. And then they could determine their speed v through space. But nope, that's not possible. If they could measure their speed through space, they could synchronize their clocks truly. But they can't do either one. Now, Einstein and Lorentz, they didn't have our constructive model. But on the macro scale, Einstein still recognized these facts about synchronization, and he decided that the most logical approach is to synchronize clocks such that the speed of light will be measured to be the same in all directions. So he was quite aware of this issue. And here's the quote of Einstein on this topic. He said that light requires the same time to travel the distance from A to M as from B to M is in reality neither a supposition nor a hypothesis about the nature of light, but a stipulation which I can make of my own free will in order to arrive at a definition of simultaneity. And I think that's awesome. It's a brilliant decision. But I also chuckle on this point because, personal story, back in the 80s, I was in engineering in grad school, but I sat in on some lectures in the literary criticism over in the English department, and when they were having lectures on a thing called deconstruction, they would pick apart some classic text of somebody, and they would try to burrow down to find just the exact words where, if they picked it apart, everything collapsed. And that was called deconstructionism. And so here's my joke, if this video series was called Deconstructing Relativity, this is the paragraph I would go to right here. Because just think it's funny. He says, it's a stipulation which I could make of my own free will. Well, a stipulation is usually an agreement between two different people, like lawyers. I'm going to stipulate, yeah, I'll stipulate that that's true. But here he's making a stipulation with himself, apparently. But in actual fact, it was brilliant. It's a beautiful thing, and I'm not here to deconstruct it. I'm here to reconstruct it. So let's go out. As always, thanks for watching. It's my book. It's on Amazon. Like, subscribe, share if you want. And as always, a relevant and interesting music clip to go out on. Catch you next time.
Don't surround yourself with yourself. Move on back to squares. Send an instant comment to me. Initially